Time is something we all experience every day, and it feels constant. A second ticks by the same way whether we are awake or asleep, walking or sitting still. But that is only how it feels in our everyday life. Physics tells us a different story. Time is not universal. It does not flow the same for everyone, everywhere. Its pace depends on motion, on speed, on how fast you are moving relative to something else. This is one of the most surprising and counterintuitive aspects of our universe. To make this concrete, imagine standing on a train platform, watching a train rush past. Inside the train, passengers are sipping coffee, reading newspapers, and checking their watches. To them, the clock ticks normally. To you, standing still on the platform, those same clocks appear to tick slower. Every second for the passengers seems stretched out from your perspective. This effect is called time dilation, and it is a direct consequence of the way space and time are connected in Einstein's theory of special relativity. Time dilation is not just a theoretical idea. It has been observed repeatedly. Atomic clocks flown around the world on airplanes run slightly slower than identical clocks that remain on the ground. Particles called muons, created when cosmic rays strike the atmosphere, decay more slowly if they are moving near the speed of light, allowing them to reach the surface of Earth even though their lifetime is very short. These are precise, measurable consequences of the laws of physics, showing that motion affects the flow of time. The key idea is that time is flexible. It can stretch or contract depending on your velocity. The faster you move, the more pronounced the effect becomes. At everyday speeds like walking, driving, or flying, the effect is extremely tiny, so tiny that we don't notice it. But as you move closer to the ultimate speed limit of the universe, the speed of light, the difference becomes enormous. Clocks slow dramatically. Your heart beats more slowly compared to a stationary observer. And even the simplest processes, like making a cup of coffee, would appear to drag from the perspective of someone watching from outside. To see how extreme this can get, consider a spaceship accelerating to a speed approaching light. For the people on board, time seems to flow normally. Their coffee steams, their watches tick, their conversations unfold. But for someone remaining behind on Earth, every second aboard that spaceship stretches out. Minutes, hours, and years appear to slow down relative to the stationary observer. The closer the spaceship comes to light speed, the slower time passes relative to Earth. And mathematically, if an object could actually reach the speed of light, time would stop entirely for that object relative to any stationary observer. This is where intuition begins to fail. Our brains evolved to process life at walking speeds and moderate distances. We have never experienced velocities anywhere near light speed. We have never experienced time slowing or freezing. That is why it is difficult to internalize. The everyday flow of seconds and minutes seems absolute to us, but physics shows that it is not. Time is a dimension connected to space, flexible and relative, and it depends on how you move. What feels like a constant river to us is, at high speeds, a malleable fabric stretching and bending in ways our instincts cannot predict. The profound implication is that time is not a universal stage on which events unfold. It is part of the very structure of reality, changing with motion. Clocks aging and the passage of events are not absolute. They are local, dependent on your velocity relative to others. Time is not something separate from the universe. It is part of the universe shaped by the geometry of space, motion, and the fundamental laws of physics. This is the first step in understanding why time can literally freeze at the speed of light. A concept that is mathematically rigorous as it is counterintuitive. It is a reminder that the universe is far stranger than our everyday experience suggests, and that what feels familiar, seconds, minutes, hours, is only a local illusion shaped by motion and perspective. As we begin to move faster and faster, approaching the speed of light, the effects of time dilation become more extreme and astonishing. Imagine you are inside a spaceship traveling close to light speed. Everything inside the ship feels completely normal. Your coffee swirls, your watch ticks, your heart beats steadily, and your conversations unfold just as they always have. From your perspective, time is flowing exactly as it should. But if someone were observing your spaceship from a stationary location, the situation looks entirely different. They would see your movement slow down dramatically. Every tick of your clock would stretch out, every heartbeat would take longer, and even simple actions like stirring coffee would appear to happen in slow motion. This is the heart of special relativity motion, changes the flow of time. The faster you move relative to someone else, the slower your time passes from their point of view. This is not an illusion, nor is it a trick of perception. It is a physical effect, measurable and predictable. It has been confirmed in countless experiments, from flying atomic clocks around the world to observing high-speed particles in accelerators. Time, it turns out, is not universal. It is relative, dependent on motion, and it stretches or contracts depending on how fast you move. The mathematics of this effect is encoded in the Lorentz factor, which describes exactly how much time slows for a moving observer. As your speed approaches the speed of light, the factor grows without limit. Time dilation becomes enormous. If it were possible to reach the speed of light, a hypothetical scenario for objects with mass, time would completely stop relative to any outside observer. This is not science fiction. It is a direct consequence of the geometry of space and time as described by Einstein. To visualize this, imagine time as a river flowing steadily. A person swimming slowly across the river makes steady progress, experiencing the flow in a familiar way. As the current increases, it becomes harder to move upstream. Every stroke takes more effort relative to the riverbank, and your progress slows. Now imagine the river flowing as fast as you can possibly swim. At that point, no matter how hard you try, you are effectively trapped. You cannot advance relative to the bank. This is an analogy for approaching light speed. As your velocity increases, time for you relative to a stationary observer slows. At the speed of light, time itself is frozen, and no motion through time relative to the outside world is possible. This concept can be even more mind-bending when considering distances. As speed increases, not only does time slow down, but distances in the direction of motion shrink. This is called length contraction. From the perspective of the moving observer, the universe ahead appears compressed. Together with time dilation, these effects completely change the structure of reality at high velocities. A journey that would take years for a stationary observer could be experienced as almost instantaneous for the traveler moving near light speed. Human intuition struggles to grasp this because it is built for walking speed. We evolved to navigate a world where time and space are approximately constant. Our brains cannot naturally picture time freezing or distances shrinking. We rely on metaphors, thought experiments, and mathematics to understand what happens at relativistic speeds. Visualizations like the rubber sheet analogy for spacetime help, but they cannot fully capture the strangeness of high-speed motion. The key takeaway is that time is not a universal river flowing at a fixed pace. It is a flexible dimension, intimately tied to motion. The closer we move to light speed, the more pronounced this flexibility becomes, until in the limit, time literally stops. This is the counterintuitive yet rigorously verified nature of our universe. The faster you move, the more time bends around you, until for light itself, time does not exist at all. Now let's think about light itself, because this is where time becomes truly extraordinary. Photons, the particles of light, always travel at the speed of light. Unlike you, me, or a spaceship, they cannot slow down. They are massless and therefore immune to the energy limits that prevent massive objects from reaching light speed. The consequences for time are profound. For a photon, there is no passage of time. From the moment it is emitted, whether by a distant star or a laboratory laser, to the moment it is absorbed by your eyes or a detector, the entire journey is instantaneous from the photon's perspective. There is no ticking clock, no aging, no progression of events along the path. From its point of view, the journey does not take any time at all. This idea is difficult to imagine because it contradicts everything our intuition tells us. We are used to thinking in terms of before and after, cause and effect, journeys taking time, and distances requiring effort to cross. Yet photons experience none of this. Even light that travels billions of light years across the universe does so without experiencing time. From the photon's perspective, emission and absorption are the same event. This is a direct consequence of special relativity. It is embedded in the mathematical structure of spacetime itself. To visualize this, consider a thought experiment. Imagine a photon leaving a star located millions of light years away. In human terms, that light takes millions of years to reach us. Billions of generations of stars may form and die during that time. Yet for the photon, all of that history happens instantly. The photon does not age, and its journey does not exist as a sequence of events. This is not science fiction. It is the natural result of how time behaves at light speed. Humans struggle to internalize this because our brains are wired to experience the slow, steady flow of seconds and minutes. We have never experienced motion close to the speed of light. We cannot perceive time slowing down, let alone freezing entirely. Our intuition is tied to the world of moderate speeds and ordinary scales. Trying to picture the universe from the perspective of light feels almost impossible. Even our best analogies, like stretching a rubber band to represent time dilation or compressing a spring to represent length contraction, fall short when it comes to fully conveying what it means for time to stop entirely. Yet physics allows us to explore these extreme scenarios mathematically, and experiments confirm the predictions indirectly. Particle accelerators routinely propel subatomic particles to speeds very close to light. Their lifetimes, measured in the lab, increase exactly as predicted by time dilation. Cosmic rays from distant space behave in ways that demonstrate time and distance are not absolute. Light's instantaneous experience of time is a limiting case of these measurable effects. Understanding that time literally freezes at light speed forces us to rethink the nature of reality. Time is not a universal, unchanging river. It is a flexible dimension entwined with space and motion. Every observer experiences a different flow of time depending on their velocity. The faster you move, the slower your clock ticks relative to someone at rest. At the ultimate speed, the speed of light, time ceases to flow altogether. This has profound implications for our view of the universe. It means that the events we observe, even those that seem to take billions of years, can occur in a framework where time is not universal, where the notions of before and after are relative, and where the universe itself behaves in ways far removed from everyday experience. It challenges our deepest intuitions and reveals the astonishing, counterintuitive structure of spacetime that governs everything, from the smallest particles to the most distant galaxies. To understand why humans struggle to fully grasp the freezing of time at light speed, we need to examine the way our brains evolved and how we experience the world. Human intuition is built around walking, running, and navigating environments where speeds are tiny compared to the speed of light. We experience a nearly constant flow of time and assume that the sequence of events is universal. A second passes the same for everyone, everywhere. That assumption works perfectly for daily life, which is why it feels natural. But the universe is far larger and stranger than what our senses evolved to perceive. When we approach extreme velocities, the familiar rules no longer apply and our intuition breaks down. Even imagining traveling at relativistic speeds stretches the mind. Suppose you could accelerate a spaceship to 99% of the speed of light. Time inside the ship slows, dramatically relative to someone stationary on Earth. A journey that might seem to take years for a passenger on board could appear to take decades or centuries to someone observing from a distance. Trying to picture that discrepancy is difficult because we have no real world analogs. We are used to clocks that tick uniformly, but at near light speeds, the concept of simultaneous events itself becomes relative. What seems now to the traveler is not the same, to an observer at rest. Our brains have no built-in mechanism to intuitively process multiple flows of time occurring simultaneously from different perspectives. We also struggle because visual metaphors can only go so far. Scientists often use diagrams like the rubber sheet analogy to illustrate spacetime, or arrow stretching to represent time dilation. These help to convey general ideas, but cannot fully capture the experience of extreme velocities. Length contraction, where distances shrink in the direction of motion, combines with time dilation to create a reality that is alien to everyday perception. Objects moving close to light speed do not just age slower, they literally perceive distances differently. From the traveler's perspective, a journey across the galaxy could take only a fraction of the time that it seems to take to someone at rest. This simultaneous distortion of time and space is deeply counterintuitive, yet it is mathematically precise and experimentally verified. Another source of difficulty is that no massive object can ever reach the speed of light. The equations tell us what would happen in that limit, but we cannot physically experience it. We can accelerate particles to incredible speeds in laboratories, but even then, they are still not moving at light speed, so we cannot directly observe a complete freezing of time. This makes the concept feel abstract, theoretical, or even paradoxical, even though it is a real and unavoidable consequence of special relativity. The struggle also stems from language itself. Everyday words like time, now, and instant imply uniformity and continuity. Physics demands precision. Time is a dimension intertwined with space, and it can stretch, shrink, and freeze depending on relative motion. Our natural vocabulary does not convey these subtleties. To communicate relativistic effects, we must rely on mathematics, thought experiments, and careful analogies. Even then, the reality remains difficult to internalize fully. Finally, understanding the freezing of time challenges not just intuition, but deeply held conceptual frameworks. It overturns the idea of a universal clock, replaces it with a relative and flexible flow of time, and reveals a universe that is stranger than everyday experience allows. Recognizing this requires humility and imagination. It demands accepting that our senses and instincts are inadequate for grasping the true behavior of nature at its extremes. Yet by studying these limits, we gain a deeper appreciation for the structure of reality and the profound ways in which space, time, and motion are interconnected. To get a more intuitive sense of how time behaves at high speeds, it helps to use thought experiments and analogies that relate to our everyday experiences. Imagine time as a river flowing steadily. For most of us, swimming across the river is straightforward. You move through the water, and you experience each moment as it passes. The river's current is slow enough that it doesn't significantly affect your motion, and your perception of time feels constant. But now, imagine the river's current increases dramatically, moving faster and faster. As you swim upstream, you notice that your progress relative to the riverbank is slower. Every stroke takes more effort, and your journey takes longer than you expect. Time is no longer uniform. It stretches under the influence of relative motion. As the current grows ever stronger, approaching an impossible speed, your ability to move forward relative to the bank diminishes. No matter how fast you swim, you are dragged along by the river. This is analogous to approaching the speed of light. In relativity, the faster you move relative to another observer, the slower your time passes from their perspective. As your speed approaches the ultimate cosmic limit, time dilation increases without bound. If you could reach the speed of light, which is impossible for objects with mass, the river would be flowing infinitely fast. You would be trapped in the current, and time would completely freeze relative to anyone at rest. From the traveler's own point of view, however, everything inside their frame would feel perfectly normal. The coffee still swirls, clocks tick, and conversations continue. This thought experiment helps us visualize why time freezing at light speed is so counterintuitive. We naturally expect time to flow uniformly, but relativity tells us otherwise. Our intuition is built for a world where velocities are tiny compared to the speed of light, and the effects of motion on time are negligible. That is why imagining extreme speeds approaching light speed is so difficult. Time is no longer the constant river we experience in daily life. It becomes a flexible, stretching dimension, intimately tied to motion. Another surprising consequence of approaching light speed is length contraction. Just as time stretches, distances in the direction of motion shrink from the perspective of an outside observer. From the traveler's point of view, the universe ahead compresses. A journey that seems to take decades to someone at rest could be completed in what feels like mere years to the traveler. Time dilation and length contraction together create a universe that behaves in ways that are completely alien to our everyday experience. Yet the mathematics describing these effects is precise and rigorously verified. These phenomena are not just theoretical. They have real, measurable consequences in experiments and technology. Particle accelerators routinely propel subatomic particles to speeds close to light. Their observed lifetimes extend exactly as predicted by time dilation. Cosmic rays traveling at near light speeds reach the surface of Earth in numbers consistent with relativistic predictions. GPS satellites orbiting Earth at high speeds and experiencing weaker gravity than the surface require precise adjustments to account for time dilation effects. Without these corrections, the system would quickly become inaccurate. These examples show that the flexible nature of time is not an abstract curiosity, but a concrete feature of the universe. Visualizing time as a river with a speeding current, combined with the compression of distances at high speeds, helps us grasp the seemingly impossible idea that time can literally freeze. It allows us to translate abstract mathematics into an intuition, however limited, that makes the consequences of relativity tangible. Time is not a universal constant. It is a dimension that responds to motion, stretching, contracting, and even halting entirely in extreme scenarios. Through these thought experiments, we can begin to understand a universe that behaves in ways far stranger than our instincts suggest, yet consistently and beautifully, according to the laws of physics. As we explore the consequences of time dilation and length contraction, it's important to understand why no object with mass can ever reach the speed of light. The universe sets an ultimate speed limit, and it is absolute nothing with mass can cross it. The reason lies in energy. As an object moves faster, its relativistic mass effectively increases, meaning it requires more and more energy to continue accelerating. Near light speed, the energy required grows enormously. To actually reach the speed of light would require infinite energy, which is impossible. This is not a limitation of our technology. It is a fundamental law of physics. Despite this limitation, studying objects moving close to light speed reveals the extreme consequences of relativity. Imagine a spaceship accelerating to 99.9% of the speed of light. From the perspective of someone on board, time seems entirely normal. A cup of coffee swirls, watches tick, and people converse without noticing anything unusual. But from the perspective of someone stationary outside the ship, the traveler's clock is moving incredibly slowly. Every second on board corresponds to minutes, hours, or even years outside. The faster the ship goes, the more pronounced this effect becomes. This illustrates that the flow of time is not universal. It is relative, dependent on motion. High-energy particle experiments provide tangible examples of these effects. Subatomic particles accelerated in laboratory facilities approach the speed of light. Observed from the lab, their decay times increase precisely according to the predictions of special relativity. Cosmic rays traveling through space experience similar effects, allowing particles that would normally decay in microseconds to reach the surface of Earth. These observations confirm that time dilation is not a theoretical curiosity. It is an experimentally verified aspect of reality. The equations that predict time slowing at high speeds are the same equations that describe light and particle behavior throughout the cosmos. Length contraction is another direct consequence of moving at high speeds. From the stationary observer's point of view, objects moving near light speed appear compressed along the direction of motion. A journey across the galaxy that would take thousands of years for someone at rest could feel almost instantaneous for a traveler moving at near light speed. This combined with time dilation shows just how differently reality behaves at extreme velocities. Space and time are not fixed arenas, but interconnected dimensions. that respond dynamically to motion. Human intuition struggles to grasp this because we evolved to perceive a world where velocities are extremely small relative to light speed. We experience time as a constant, uniform flow, and distances as fixed. There is no natural way for our senses to perceive hours stretching into years or distances shrinking across the universe. We must rely on mathematics analogies and thought experiments to understand these extreme scenarios. Visualizations such as a river representing time or a compressed ruler representing length contraction help, but they only scratch the surface of the true phenomena. Despite our inability to directly experience time freezing, the implications are profound. The fact that motion affects the passage of time changes our understanding of reality itself. It shows that what we perceive as normal, time is just one perspective, and there exist other frames of reference where time flows differently. The universe is not absolute in its measurement of seconds and minutes. It is a flexible structure where time and space are intertwined, bending and stretching according to motion. Approaching the speed of light reveals the ultimate malleability of these dimensions and hints at the astonishing behaviors of the universe that lie beyond ordinary experience. As we continue to explore the strange effects of traveling near the speed of light, the broader implications for reality begin to emerge. Time is not an independent universal entity. It is deeply linked with space, and both are affected by motion. What we consider to be the present is not the same for all observers. Events that appear simultaneous to one person may occur at different times for someone moving at a different speed. This idea may seem abstract, but it has real consequences even in practical technologies. For example, GPS satellites orbiting Earth move at high velocities and experience weaker gravity than the surface. Both velocity-based time dilation and gravitational time dilation occur simultaneously. Engineers must account for these effects to ensure that positioning signals remain accurate. Without corrections for the relative flow of time, GPS systems would quickly become unreliable, illustrating that relativistic effects are not just theoretical, they are part of our everyday lives. When we consider motion near the speed of light, time itself becomes a flexible, local quantity rather than a universal backdrop. Imagine a traveler moving close to light speed on a journey across the galaxy. From the traveler's perspective, the journey may take only a few years, even though millions of years might pass for someone remaining on Earth. The faster the traveler moves, the more extreme this effect becomes. Distances in the direction of motion also shrink due to length contraction, allowing the traveler to traverse vast cosmic distances in what feels like a brief period. These phenomena highlight the interconnectedness of space, and time motion alters both. And the universe cannot be described independently of the observer's frame of reference. This relativity of time challenges our most basic assumptions about the universe. Our daily experience teaches us that time is steady and predictable, flowing at the same rate for everyone. Special relativity shows that this is only an approximation, valid at the slow speeds we encounter in daily life. At high velocities, our intuitive sense of time breaks down. A second for one observer may be an hour, a year, or even longer for another observer moving differently. The idea that no is not absolute forces us to reconsider how events are ordered across space. Cause and effect remain consistent locally, but the perception of simultaneity depends on motion. Even light itself demonstrates the extremes of these principles. Photons travel at light speed and experience no passage of time at all. From the photon's perspective, emission and absorption are a single instant. Events separated by billions of years in light. Years occur instantaneously in its frame. This challenges our ordinary notions of before and after. The universe, when viewed at these extremes, behaves in ways that defy human intuition yet are internally consistent and mathematically precise. Understanding that time is relative also leads to profound philosophical implications. It suggests that reality is not a fixed stage on which events unfold uniformly, but a dynamic network of perspectives, each defined by motion. The past, present, and future are not universal coordinates, but local experiences. This perspective forces us to question the very nature of now, and realize that our ordinary experience of time is only one of many possible flows. The cosmos is a complex tapestry of local clocks moving and stretching relative to one another. Ultimately, studying time dilation at near light speeds transforms our understanding of the universe. It shows that time is not a passive backdrop, but an active participant in the structure of reality. The passage of seconds is relative. Distances are malleable, and the universe is far stranger than our instincts suggest. This insight reshapes not only physics, but our perspective on reality, revealing a cosmos where motion, space, and time are inseparably linked in ways that challenge and enrich human understanding. The more we explore the consequences of time, behaving differently at high velocities, the more it challenges our everyday understanding of reality. Time, as we experience it, seems constant and uniform. A second passes the same way for us, whether we are sitting at a desk or walking down the street. But as we have seen, this perception is limited to the relatively slow speeds and small distances we encounter in daily life. When motion approaches the speed of light, the flow of time changes dramatically. Seconds stretch into minutes, minutes stretch into hours, and eventually, if you could reach light speed, time itself would stop relative to any outside observer. Length contraction is another facet of this phenomenon, and it works hand in hand with time dilation. Distances in the direction of motion shrink as speed increases. A journey that seems to take millions of years from the perspective of a stationary observer could feel almost instantaneous to someone moving at near light speed. Space itself, like time, is not absolute. It bends and compresses in response to motion, revealing that our familiar sense of distance is only valid at everyday speeds. This interconnectedness of space and time forms the basis of spacetime, a unified structure in which motion determines both how time flows and how distances are measured. Thinking about these effects can feel like stepping into a science fiction scenario, but they are fully supported by experimental evidence. Particle accelerators routinely propel subatomic particles close to the speed of light. Observers measure their lifetimes and trajectories, and the results align perfectly with predictions from special relativity. Cosmic rays traveling through space demonstrate the same behavior, reaching Earth despite having lifetimes too short to survive such distances in classical terms. Even the technology we rely on, like GPS satellites, must account for relativistic effects to function accurately. This demonstrates that the slowing of time and the contraction of distances at high speeds are not abstract theories. They are real phenomena with measurable consequences. Our difficulty in imagining these effects is natural. Human brains evolved to navigate a world of slow motion and moderate distances. We have no sensory experience of time slowing down or of space compressing. Thought experiments and analogies are essential tools for building an intuitive understanding. Imagining time as a river, stretching and slowing as one moves faster, or distances shrinking like a compressible spring, helps translate the mathematics of relativity into mental pictures. Still, these tools only hint at the true strangeness of relativistic motion, where time can effectively freeze and distances contract near the universal speed limit. The philosophical implications are profound. If time is not absolute, then our notions of past, present, and future are not universal truths, but local experiences shaped by motion. Events that appear simultaneous from one perspective may not be simultaneous from another. The universe is not a fixed stage where time ticks the same for everyone. Instead, it is a dynamic network of perspectives, each defined by motion and energy. Light, traveling at the ultimate speed, experiences no passage of time, connecting distant events instantaneously. This challenges the way we conceptualize the unfolding of events across the cosmos and invites a deeper reflection on the nature of reality. The universe revealed by high-speed motion is far stranger than our daily intuition allows. Time stretches, contracts, and even freezes. Space is malleable. Distances are relative, and what we consider, is limited to our frame of reference. This perspective encourages us to see the cosmos as a web of interconnected events, each experienced differently depending on motion, yet all governed by consistent and elegant laws. By understanding time at its extremes, we gain not only scientific knowledge, but a profound appreciation for the subtle, counterintuitive, and deeply beautiful structure of reality itself. As we continue to examine the consequences of relativistic motion, it becomes clear that the universe operates on principles that defy everyday intuition. Our ordinary experience teaches us that time flows uniformly, that seconds, minutes, and hours tick by at the same pace for everyone. Yet, special relativity shows that this is an illusion. The passage of time is not fixed, it is relative, depending on an observer's motion. As one moves faster and approaches the speed of light, time slows dramatically. Approaching light speed, this slowing becomes extreme until at the ultimate limit, time itself stops. This is not theoretical speculation, it is the inevitable outcome of the laws of physics as we currently understand them. One way to conceptualize this is to imagine being on a journey across the galaxy at near light speed. From your perspective aboard the spaceship, time feels normal. Clocks tick, coffee swirls in a cup, conversations unfold, and your body ages naturally. Yet for an observer back on Earth, years might pass during what feels like days to you. The faster you move, the greater the discrepancy between your experience of time and that of someone stationary. This demonstrates that time is not universal, it is tied to motion and perspective. Our sense of simultaneity is entirely frame dependent. Events that are simultaneous for one observer may be separated by years or even millennia for another. The idea of simultaneity being relative is deeply counterintuitive because we are conditioned to think in absolute terms. In our everyday life, seconds appear constant and moments occur in a fixed order. But at relativistic speeds, the order of events and the flow of time itself depend on the observer. Light provides an extreme illustration. Photons travel at the speed of light, and from their perspective, experience no passage of time at all. Emission and absorption of a photon are effectively a single instant. For light, billions of years of travel across space are instantaneous. This collapses our conventional notions of before and after, and demonstrates how motion fundamentally alters the structure of reality. Another striking consequence is length contraction. Just as time slows, distances along the direction of motion shrink. A spaceship moving near light speed would measure a shorter distance to its destination than a stationary observer would. This contraction, combined with time dilation, reshapes the traveler's experience of space and time. A journey that seems impossibly long to an outside observer may be completed in a much shorter duration from the traveler's frame. Space and time are not separate, rigid entities, but interconnected dimensions that respond to motion. Together, time dilation and length contraction form the foundation of space-time, a unified framework in which the universe operates. Humans struggle to internalize these concepts because our brains evolved for slow speeds and moderate distances. We cannot perceive hours stretching into years or distances shrinking across the galaxy. Thought experiments, analogies, and mathematics are essential tools to build an understanding. Imagining time as a river whose flow slows relative to motion, or distances compressing like a spring under force, provides intuition, though it remains incomplete. The universe at relativistic speeds behaves in ways that challenge our deepest instincts, revealing a cosmos that is both stranger and more elegant than our everyday experience allows. Accepting this relativity of time and space requires a shift in perspective. It forces us to reconsider our assumptions about the passage of events, the meaning of simultaneity, and the nature of reality itself. Time is not absolute, space is not fixed, and motion fundamentally shapes the experience of both. By exploring these extremes, we uncover the profound structure of the universe, where each observer experiences a unique flow of time, yet all phenomena obey consistent, precise, and deeply beautiful physical laws.